This is Management 560, lecture on Chapter 5. We are talking about regression models now. So, last module, we were answering the kind of questions that you could, we were talking about statistical tests that addressed questions where we were comparing quantitative ordinal data across groups. So we were either looking at just a variable by itself, or a group, or comparing groups with each other, or comparing across multiple groups in the case of ANOVA. But we needed one quantitative ordinal variable and one categorical nominal or ordinal variable. And we didn't address the case where we have two quantitative ordinal variables, at least not directly. So you did do some work converting a quantitative variable into a categorical variable. So we took cost from restaurant in class, for example, and turned it into 4 cost categories and then ran our analysis. Well, regression models are one approach to answering questions where we have two quantitative ordinal variables, and we're interested in the relation between those variables, two or more. So what a regression model does is use simple equations to fit these relations to each other. So rather than comparing means, we're looking at how much a change in one affects a change in the other. So to do that, I'm going to just define some letters here in the equations I'm going to write. So I will use y consistently for the data we are trying to explain. So if I was thinking about what makes a bank riskier or not, well, I'm trying to explain the riskiness of a bank. So my y would be some operation of some measure of risk of a bank. So I've got here standard deviation of stock price. That'd be one way to approach it. So my y, I have the standard deviation of the stock price of a list of banks. That would be what I'm trying to explain. X, that's a stand-in letter for the data I'm using to try to explain my y. And we write y on the left and x on the right. So if my experiment is to think about, well, maybe the type of loans that a bank issues or makes, maybe the type of loans affects the risk of the bank. Some loans might be riskier than others, and so the type of loan would lead to a change in the risk. So that would mean I would be using the types of loans as an explainer of risk. So, but it has to be a quantitative ordinal variable. So that could be, for example, the fraction of total loans that were of any particular type. So, 10% farmland loans for one firm, 7% farmland loans for another, 0% for a third firm, and so on. So farmland loans out of the total, commercial loans out of the total, residential real estate out of the total, all of those could be variables that might be helpful in explaining risk. So B, or beta for doing Greek letters, that's a number chosen to minimize the error, and it's the number that defines the relation. So if for every 1% farm loans increase out of the total, so for every 1% that goes up, maybe standard deviation of stock price goes up by 0.05. Well, that would be my B. So that the B is the number that dictates the relation between those two, the explainer and the thing explained. So there's a B that corresponds to every X, no matter how many you've got going at the same time. So we'd have a B for farmland loans out of total, a B for commercial real estate loans out of total, and a B for residential real estate loans out of total. Naturally, X doesn't perfectly explain Y. And so even if when one of my X's goes up, Y goes up, or when X goes up, Y goes down, that's not going to do a perfect job of explaining what's going on with Y. There's going to be some leftover unexplained variation in Y. So the error for any given observation is represented by E, the letter E. So if I think about, well, what if my risk level was 10 and my B is 1 and my X was 5? Well, then 5 times 1 would be 5, so my prediction for Y would have been 5, but instead it was actually 10, so I was off by 5. So error would be 5, B would be 1, X would be 5, Y would be 10. And so that would be one observation. So let's say the next observation, Y was 12 and X was 7. Well, B can't change. B is the same across all observations. But X and Y will change with your data. So X is 7, B is 1, so we are off by 5 again. So the error would still be 5, but now 7 times 1 is 7, which is 5 less than 12. So let's imagine that we are looking at the financial risk of companies, and we are going to explain that using operating risk. So how risky the fundamental business is before financing. And let's just imagine we got a 10% estimate as a baseline and 1% coefficient times operating risk. So because this number is positive, that would mean as operating risk increases, so let's say operating risk increased 1 unit, then debt as a fraction of the total, this would, so this variable is debt as a, the leverage ratio, debt as a percentage of total, that would increase by 1%, right? This goes up by 1, B2 is 1%, that means this would go up by 1%. And so we're 0.01. The implication then, if this is statistically significant, is that as risk goes up, the debt level increases, though. So the before financing risk would lead to more debt. And this is actually true, and it's a little puzzling. So it's something we're trying to figure out in business research in general. So if I have my 0.10 times x1 and 0.01 times x2, I can figure out how much I'm off in explaining y, because I can figure out what I predicted for y, that's my y hat, and what I actually got, and the difference is my error. So next we'll do an example of looking at a particular data series and building a simple model, a regression model, to explain purchases in an Amazon.com purchasing history.